Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Alcoholic KOH, ALC. KOH is a reagent that promotes dehydrohalogenation, E2 elimination, removing HX from alkyl halides to form alkenes. However, when a gamma-halocarbonyl compound, or a suitable 1,3-dihalo compound, is treated with base, intramolecular cyclization via an SN2 pathway can compete with elimination, especially when a three-membered ring can be formed. Moving on to the next step. Identify the starting material. The compound is 1,7-dichloroheptane, 4-1, Cl CH2CH2CH2C is equal to O, CH2CH2CH2 Cl. The carbonyl is at C4 with 3 carbon chains bearing Cl at each end, C1 and C7. Moving on to the next step. Consider the role of ALC. KOH, 2 moles. Alcoholic KOH can act as a base for elimination or as a nucleophilic base that deprotonates alpha to the carbonyl. The alpha carbons to the ketone are C3 and C5. Deprotonation at C3 generates an enolate which can displace the Cl at C1 intramolecularly. C1 is 3 atoms away from C3 forming a 3-membered ring, C1, C2, C3 cyclases to give a cyclopropane ring on one side of the ketone. Similarly, deprotonation at C5 generates an enolate which displaces Cl at C7 intramolecularly to form another cyclopropane ring on the other side. And for the final step, first equivalent of KOH deprotonates C3, alpha to ketone, the enolate carbon, C3, attacks C1, bearing Cl, in an intramolecular SN2, displacing Cl and forming a cyclopropane ring fused to the ketone on the left side, giving cyclopropyl C is equal to O, CH2CH2CH2Cl. Second equivalent of KOH deprotonates C5, alpha to ketone in the intermediate, the enolate carbon attacks C7 intramolecularly, displacing the second Cl and forming the second cyclopropane ring. Cyclopropyl C is equal to O, cyclopropyl, which corresponds to option B. Why other options fail? Option A. Simple double dehydrohalogenation would give divinyl ketone only if elimination occurred, but with ALC. KOH and a gamma-chloroketone, intramolecular cyclization, forming cyclopropane, is strongly favored over intermolecular elimination because the enolate is an excellent intramolecular nucleophile at the gamma position. Option C. This would require a different elimination pattern inconsistent with the structure. Option D. Aqueous KOH, nucleophilic substitution with OH would give the diol, not alcoholic KOH, which favors elimination cyclization. Therefore, the correct answer is B. Therefore, the correct answer is option B.